Hi everyone, so I'm here to do another AP Physics C for your response. This one is from 2009 and it's ENM3. I redrew the diagram right there and I'll read the question. A square conducting loop of side L contains two identical light bulbs 1 and 2 as shown. There is a magnetic field directed into the page in the region inside the loop with magnitude as a function of time t given by B equals AT plus B, where A and B are positive constants. The light bulbs each have constant resistance R initial. Express all answers in terms of the given quantities and fundamental constants. A. Derive an expression for the magnitude of the nth generated in the loop. Okay, so this is a diagram right there, and we'll start over here. So part A. They want to know the nth. So we know that nth equals d flux dt. And that's just by Faraday's law. But then we know that flux is equal to BdA, or the magnetic field times the area. So I'll just write it again over here, flux, and then d dt of BA. So now we can write this as A times dB dt, because they give us the rate that the magnetic field is decreasing over time. And that's just the formula. So we have A times AT plus B, or the derivative of that actually. Because they gave us that the B equals this formula. So then we just take the derivative of that and we get A times A. And then the area is just equal to the length squared, because the squared is of side L. So we have L squared A. And that is equal to the nth. Okay. Part B. Determine expression for the current through bulb 2. Okay, so B, and bulb 2 is right there. Okay, so they want to know the current. So we can start again from V equals IR. Then we can solve for the current, so I equals V over R. Now over here, the amp, we just found the voltage, so we can just write A times L squared. Now we have to divide by the resistance. The resistance, however, we know is our initial for one of the light bulbs. We want to know the resistance, the current through this one, so you have to include both of them. So we would have 2 R initial, and that is the current. Indicate on the diagram above the direction of the current through bulb 2. Okay, so again, for now the direction of the current, we have to use the right-hand rule. So we know that the magnetic field is into the board, and it's increasing. However, the current's not happy, and it's going to want to increase out. So increase out, and then our fingers curl in the direction of induced current, which is counterclockwise. So basically, we could just draw over here. A counterclockwise current. So just right here, counterclockwise. Okay. C. Derive an expression for the power dissipated in bulb 1. Okay, so power, we know, equals IV. And I, we just figured out above. So we have AL squared over 2R initial. And now we want to know, you have to multiply that by V. And V would be A L squared over 2, because this is the nth for the total circuit, but we want to know it just for one of the bulbs, so we have to divide by 2, and then we get that. So then when we figure this out, we get A squared L to the 4th divided by for our initial. Okay, so that is the power dissipated. Now, another identical bulb, 3, is now connected in parallel with bulb 2, but is entirely outside the magnetic field as shown. So this is the diagram they have. D. How does the brightness of bulb 1 compare to what it was in the previous circuit? Is it brighter, dimmer, or the same? Explain. Okay, so now we have another bulb connected in parallel. And we know that whenever there's connections in parallel, the equivalent resistance can never be greater than one of the individual ones. That means by adding this in parallel, we actually decrease the resistance. So over here, if we have D, we have V equals IR. Because it's connected in parallel, we know that the voltage stays the same because parallel V par V. So if this is constant, and I just said that the resistance is going to decrease, that means the current is going to increase to make the voltage the same. Now if we have power equals IV, and this stays the same, but the current is increasing, that means the total power is also increasing. And if power is increasing, the brightness will also increase, and that's why bulb 1 will now be brighter than what it was. So again, you decrease the resistance, but you increase the current. Increased current gives a bigger power, thus making it brighter. Okay, yeah, so that's it for this free response. I hope it helped, and I will see you later. Bye!